52 million years ago, there was no Arctic, not as we know it. In its place stood a rainforest so vast, so alive, and so unlike anything that exists today that the fossils it left behind still stop scientists in their tracks. The Arctic was not always frozen. The ice came very much later. It was a very warm world, not slightly warmer than today, not warm enough to merely survive in, warm enough for rain to fall in sheets through a closed canopy, warm enough for slow, dark rivers to wind between the roots of redwoods and magnolias, warm enough for the air above those rivers to move with living things, a full, roaring ecosystem sitting where today there is nothing but ice and silence. And the things living in it were extraordinary. Alligators lived here, not as seasonal visitors drifting north in summer, as permanent residents, breeding, hunting, overwintering, in rivers that today sit frozen under meters of ice. Giant tortoises moved through the undergrowth. Large constricting snakes threaded through warm Arctic swamps. Creatures that looked and moved like primates made their home in this forest, in the northernmost habitat of any primate like animal ever found in the fossil record. Then there is the detail that makes all of it stranger still. Every winter, the sun disappeared. Completely. For months. Total darkness in a forest full of predators, full of warm rivers, full of life that had no equivalent anywhere on Earth before or since. This world is not theory, it is not speculation. Beneath the permafrost of Ellesmere Island in Canada's high Arctic, seams of coal run through the bedrock. Coal is compressed forest. Every seam is the pressed, blackened remains of trees that once stood in that exact place, their roots in warm soil, their canopy catching rain. The Arctic is not remembering a story. It is holding the physical evidence of one, a world that had endured for millions of years. Then it vanished. The forest disappeared, the animals disappeared. Only the rock remained, preserving the story beneath layers of ice that would one day convince the world this place had always been frozen. In this story, we're returning to the Arctic as it existed before the ice, to uncover how a rainforest flourished at the top of the world, why it became one of the deadliest environments on Earth, and what finally erased it from the planet. Before the Arctic carried forests, before reptiles settled into northern rivers, the planet itself had entered a different chapter. The stage for that remarkable landscape was the Eocene epoch, stretching from about 56 million years ago until 34 million years ago. It began roughly 10 million years after the disappearance of the non-avian dinosaurs and lasted for more than 20 million years, shaping a version of Earth that would seem unfamiliar even though every mountain, ocean, and continent belong to the same world. Earth has never remained locked into one climate forever. Across deep time, it has shifted between two broad conditions. One is known as a greenhouse world, where permanent polar ice is absent, atmospheric carbon dioxide remains high, and warmth extends far toward the poles. The other is an icehouse world, where large ice sheets occupy the polar regions. Temperatures remain lower, and atmospheric carbon dioxide exists in smaller amounts. Modern civilization has developed entirely during an icehouse state. The Eocene unfolded during one of the strongest greenhouse intervals in the planet's recent geological history. At the height of that greenhouse climate, global average temperatures stood roughly 36 to 54 degrees Fahrenheit warmer than those of today. Permanent ice had no place on the landscape. Antarctica supported forests instead of glaciers. The Arctic held flowing rivers instead of frozen seas. Even the highest mountain ranges lacked the enduring snowfields that have become familiar in the modern world. Heat circulated across the globe in patterns that softened the difference between tropical regions in the far north. Carbon dioxide played a central role in maintaining that balance. Concentrations in the atmosphere stood several times above the levels that existed before widespread human industry. Those gases trapped additional heat and reduced the sharp contrast between equatorial and polar regions. Energy that today escapes more readily towards space remained within the atmosphere longer, allowing warmth to spread across latitudes that now spend much of the year under deep cold. The continents also occupied slightly different positions. North America and Europe rested closer together than they do now. The Atlantic Ocean remained narrower, while stretches of dry land linked areas that have since been separated by rising seas. These broad corridors allowed plants and animals to travel between continents with remarkable freedom. Forest expanded across connected landscapes, and entire communities of mammals, reptiles, and birds followed climates that stretched across regions now divided by open water. Nothing about this arrangement required different laws of nature. Gravity remained unchanged. Sunlight followed the same daily rhythm. The rocks beneath every forest formed from the same minerals found across the planet today. Only the atmosphere, ocean circulation, and continental geography combined in a different balance, producing a climate that allowed rainforests to flourish near the pole and creatures usually associated with warm wetlands to occupy places now covered by snow and ice. The Eocene therefore belongs to neither fantasy nor speculation. It represents one documented configuration of Earth's climate system, preserved in sediments, fossils, and ancient chemistry with extraordinary consistency. That world provided the setting upon which the Arctic rainforest flourished, waiting for a powerful chain of events that transformed the atmosphere and reshaped the course of life across the entire planet. Every climate has a beginning, a moment when familiar balance gives way to something entirely different. For the Eocene world, that turning point arrived about 55.8 million years ago during an event known as the Paleocene-Eocene Thermal Maximum. The name is lengthy, though the transformation it describes unfolded with startling speed by geological standards, marking one of the most dramatic climate shifts preserved in Earth's history. Measured against a human lifetime, 10,000 years seems immeasurably long. Measured against the age of the planet, it passes almost like the turning of a single page. Within that brief geological interval, average global temperatures climbed by roughly 16 to 25 degrees Fahrenheit. Oceans warmed, weather patterns changed, and ecosystems across the world found themselves adjusting to conditions unlike those that had existed only a short time before. Scientists continue to study exactly how this remarkable warming began, yet the leading evidence points toward immense volcanic activity as the North Atlantic Ocean slowly opened. Great eruptions released enormous quantities of carbon from deep within the Earth. That initial pulse may have disturbed frozen methane trapped beneath ancient seafloors. As methane escaped into the atmosphere, additional warming encouraged even more release, creating a self reinforcing cycle that strengthened the original change and carried it much farther than volcanic activity alone might have achieved. Its influence reached every corner of the globe. Near the North Pole, the surface of the Arctic Ocean warmed to about 73 degrees Fahrenheit, conditions resembling tropical coastlines far to the south. Waters that now spend much of the year sealed beneath floating ice instead carried warmth across northern latitudes. Heat spread through ocean currents and the atmosphere together, allowing climates that once seemed impossible to become established across regions usually associated with severe cold. Living communities responded in different ways. Far below the ocean surface, many organisms adapted to stable temperatures, struggled as warmer water and increasing acidity altered the chemistry around them. Numerous deep sea species disappeared from the fossil record during this interval. On land, mammals followed another path. Fossil skeletons reveal that several groups became noticeably smaller. Reduced body size appears to have helped them cope with hotter conditions, while plants, altered by rising carbon dioxide, offered food with lower nutritional value. Although the Paleocene-Eocene Thermal Maximum endured for roughly 200,000 years, the world that emerged afterward never fully returned to its earlier state. Temperatures eased from their highest peak, yet the atmosphere remained warm enough to sustain the prolonged greenhouse climate that defined the early Eocene. Forests expanded, habitats shifted, and the conditions that later supported life far within the Arctic gradually became established across the northern continents. One comparison deserves careful attention because it places this ancient event into a broader perspective. Geological evidence indicates that the immense release of carbon unfolded across roughly 10,000 to 20,000 years. Human industrial activity has added comparable amounts of carbon to the atmosphere within about 200 years. Those figures stand side by side without requiring embellishment, linked across millions of years by the same physical processes that govern the atmosphere today. From that immense release of carbon came an altered planet whose history remained written in stone, water, and living tissue, leaving behind the conditions that shaped the remarkable Arctic world preserved in the fossil record. Climate does not spread across a planet like paint across a canvas. It moves through currents, winds, sunlight, and water, each influencing the next until an entirely new pattern emerges. After the great release of carbon reshaped the atmosphere, the most profound transformation unfolded at the highest latitudes, where the distinction between the tropics and the pole gradually faded into something Earth no longer experiences. Under ordinary conditions, the planet maintains a strong temperature contrast between the equator and the polar regions. That difference powers the great belts of wind that circle the globe, steering storms and guiding moisture from one continent to another. During the early Eocene greenhouse world, this contrast weakened dramatically. The poles warmed much faster than lower latitudes, reducing the sharp thermal boundary that normally organizes global weather. Climate scientists describe this process as polar amplification. In a greenhouse world, warming removes reflective ice and snow, exposing darker ocean water and land. Those darker surfaces absorb more sunlight instead of sending it back into space. As additional heat accumulates, even more reflective ice disappears, reinforcing the warming already underway. The cycle feeds upon itself, making the polar regions especially responsive whenever atmospheric carbon dioxide increases. As the temperature difference diminished, the atmosphere behaved differently. Air carrying warmth and moisture no longer remained confined near tropical regions as effectively as it does today. Broad circulation patterns relaxed, allowing humid air masses to travel much farther north. Clouds formed over landscapes that had once been comparatively dry, and rainfall reached places where modern climates struggle to support even scattered vegetation. The Arctic Ocean changed alongside the atmosphere. Warmer surface waters released heat throughout the year, especially during the darker months when sunlight vanished. Air passing across those waters reached nearby land already moderated, preventing the severe winter cold that dominates the modern Arctic. Seasonal cooling still occurred, though temperatures hovered close to the freezing point instead of plunging toward the deeply frigid conditions familiar today. That steady moderation became one of the defining features of the northern climate. Ocean circulation also followed a different rhythm. Modern oceans rely upon dense, cold polar water sinking into the deep sea, helping drive a worldwide conveyor of moving currents. Without extensive polar ice and extremely cold surface water, that circulation weakened and shifted into patterns unlike those operating today. Heat lingered longer in northern waters, spreading across broad marine regions before gradually dispersing elsewhere around the globe. The outcome extended far beyond pleasant weather. Landscapes near the top of the world remained above freezing throughout the year, even though modern winter temperatures in those same locations often approach 40 degrees below zero Fahrenheit. Rivers continued flowing, soils avoided prolonged freezing, and growing seasons stretched long enough for forests to establish deep root systems. Conditions that currently define temperate regions became established at latitudes where ice now dominates nearly every aspect of life. Nothing about the Arctic stood apart from the rest of the greenhouse planet. It represented the place where every climatic process reached its fullest expression, where warming accumulated most efficiently and reshaped the environment with exceptional completeness. Across those transformed northern lands, expanding habitats invited plants and animals to extend their ranges, following warmth that had reached the very edge of the world. Maps can disguise extraordinary histories. Ellesmere Island now appears as a pale shape at the northern edge of Canada, surrounded by frozen seas and long winters. Its modern landscape is among the harshest on Earth, with broad ice fields covering roughly 2,400 square miles and temperatures that can descend to about 40 degrees below zero Fahrenheit. Vegetation is sparse, trees are absent, and much of the ground remains locked within permafrost for most of the year. 52 million years ago, the same island presented an entirely different face. Instead of exposed rock and drifting snow, it formed a broad lowland of wetlands, forests, rivers, and shallow swamps. Rain fell often enough to sustain dense vegetation across the landscape, feeding soils that remained moist through much of the growing season. Annual rainfall has been reconstructed at roughly 39 to 55 inches, placing this northern forest alongside some of the wettest, temperate regions of modern North America. Those figures become even more striking when placed beside familiar places. Seattle, Washington receives about 38 inches of rain during a typical year. Portland, Oregon averages roughly 43 inches. The Eocene forest on Ellesmere Island matched or exceeded both. Such rainfall supported a thriving ecosystem where towering trees, broad-leafed plants, and water-loving vegetation shared the same landscape for millions of years without interruption from prolonged freezing. Scientists reached these conclusions through the work of paleobotanists, researchers who specialize in fossil plants. Fossil leaves preserve remarkable clues about the climates in which they once grew. Their size, shape, edge, structure, and networks of veins all reflect long periods of adaptation to temperature and moisture. By comparing these preserved leaves with living relatives growing under known conditions, researchers can estimate rainfall with surprising precision. Thousands of fossil specimens together reveal the character of an entire vanished environment. The island itself occupied nearly the same latitude that it does today, resting at roughly 76 to 77 degrees north. It remained well above the Arctic Circle, receiving the same annual cycle of continuous summer daylight and extended winter darkness that defines the region today. Geography had changed very little. Climate had changed almost everything. The warmth belonged to the atmosphere rather than to continental movement, making the forest one of the clearest demonstrations that latitude alone does not determine climate. Another source of evidence came from fossil teeth. The chemistry preserved within their enamel records, the temperatures of the water animals drank while the teeth were forming. Analyses from several different mammals converge on nearly identical values. The warmest months averaged about 66 to 68 degrees Fahrenheit, while the coldest months remained near 32 to 38 degrees Fahrenheit. Winter approached freezing but rarely crossed into conditions that would persistently lock rivers beneath thick ice. That narrow temperature range shaped the entire ecosystem. Cold-blooded reptiles could survive every season without retreating to warmer latitudes because lethal freezes failed to arrive. Rivers continued flowing, wetlands remained active, and food webs persisted through the changing light of the year. The richness of life reflected those favorable conditions. Fossils representing at least 25 distinct mammal genera have been identified from Ellesmere Island alone. Such diversity belongs to a mature, stable ecosystem with many ecological roles already filled, revealing that this northern rainforest stood among the most successful biological communities of the early Eocene world. Temperature alone cannot explain the Arctic rainforest. One final piece transforms the entire picture from unusual into almost unimaginable. Even during the warmest years of the early Eocene, the northern sky still obeyed the same geometry that governs it today. The Earth leaned upon its axis exactly as it does now, carrying the highest latitudes through months when the sun never climbed above the horizon. Ellesmere Island rested at roughly 77 degrees north, well inside the Arctic Circle. Its forests enjoyed continuous daylight during summer, yet every year that abundance came to an end. Autumn arrived. The sun slipped lower each day and eventually disappeared altogether. For months, the landscape received no direct sunlight. The warmth remained, rivers continued to flow, and temperatures hovered near the freezing point, but daylight itself vanished from the forest. That annual absence of light altered every living thing. Photosynthesis stopped almost entirely once darkness settled across the canopy. Leaves could no longer capture energy from the sun, and the steady production of fresh plant growth came to a halt. The entire food web depended upon that seasonal pulse of light, so every species entered a period when resources became more limited, even though lethal cold never arrived. Cold-blooded reptiles faced a challenge unlike any experienced by their modern relatives. Alligators, tortoises, and large snakes could tolerate the mild winter temperatures because their bodies never encountered the prolonged deep freezes that would threaten survival today. Their greater difficulty came from dwindling food supplies. Fish became less active, plant growth slowed, and opportunities for hunting declined. Survival depended upon conserving energy through months when meals became far less predictable than during the season of uninterrupted daylight. Warm-blooded mammals encountered a different set of pressures. Their internal metabolism allowed them to remain active regardless of outside temperature, yet activity demanded food. As vegetation entered seasonal dormancy and many prey species reduced their movements, winter became an ecological filter. Species capable of enduring extended periods of limited resources remained established in the north. Others gradually found their suitable range farther south, where seasonal shortages were less severe. Plants themselves displayed equally remarkable strategies. Deciduous trees shed their leaves before the long darkness, reducing unnecessary water loss and conserving stored energy until sunlight returned. Evergreen conifers slowed their biological activity without abandoning their needles entirely. Growth paused across the forest, though life persisted within trunks, roots, and seeds, waiting for the first return of continuous daylight. The entire ecosystem entered a prolonged interval of reduced activity before awakening again with the northern spring. Nothing comparable exists on the modern planet. Tropical rainforests receive abundant warmth and consistent sunlight. Polar regions experience extended darkness, but remain far too cold to support forests of this kind. The Eocene Arctic combined both conditions into one stable environment, producing a climate with no true modern equivalent. Every organism living there evolved under a yearly rhythm found nowhere else before or since. For paleontologists, this contradiction has become one of the most compelling scientific puzzles preserved in the fossil record. Understanding how animals and plants endured repeated seasons without sunlight continues to reshape ideas about adaptation, resilience, and the remarkable flexibility of life when the planet itself operates under a profoundly different climate. A single walk through this forest would have crossed boundaries that no modern botanist expects to find in one place. Species that today occupy different continents and climates stood within sight of one another, rooted in the same saturated ground. The fossil record from Ellesmere Island and neighboring Axel Heiberg Island preserves that unlikely gathering with remarkable clarity, revealing a plant community assembled from combinations that the modern world keeps far apart. Among the tallest inhabitants were dawn redwoods, swamp cypresses, alders, birches, elms, and sycamores. Each belongs to lineages now associated with temperate regions, including parts of the American South, the Pacific Northwest, and temperate Europe. Their leaves, pollen, seeds, and wood appear repeatedly throughout the fossil beds, showing that these trees did not arrive as scattered individuals. They formed enduring populations that shaped the structure of the forest over countless generations. Mixed among those familiar temperate species were plants whose closest living relatives flourish much farther south. Magnolias spread broad leaves beneath the canopy, while microscopic grains of fossil pollen reveal the presence of palms. Today, palms are symbols of warm tropical and subtropical climates. Finding evidence of them above the Arctic Circle transforms the entire botanical picture. The forest brought together communities that now exist thousands of miles apart because the climatic boundaries separating them had faded from the planet. The ground itself completed this unusual setting. Water remained close to the surface through much of the year, creating an immense wetland crossed by slow rivers, marshes, and shallow pools. Tree roots anchored themselves in saturated soil where standing water collected between trunks. In many respects, the landscape resembled the great bayous of Louisiana more closely than any modern northern forest. Constant moisture encouraged rapid plant growth and supported layers of vegetation from the tallest conifers to dense shrubs and ferns below. Some of the strongest evidence still stands where it grew. At the Strathcona Fjord Fossil Forest, mineralized tree stumps remain upright within coal-bearing rock. Their roots penetrate the ancient soil exactly where they lived before burial. They were not washed there by floods or transported from distant valleys. They ended their lives in place, and over millions of years, their tissues turned to stone while preserving their original form. Visitors today can stand beside trunks that first took root more than 52 million years ago. The dawn redwood carries an especially remarkable history. For decades, scientists believed the species existed only in fossils, another branch of life's history that had vanished forever. Then, during 1944, living dawn redwoods were discovered growing in a remote valley of China. The finding transformed a fossil into a survivor. Modern groves now represent descendants of a lineage that once stretched into the high Arctic, linking present landscapes with forests separated by tens of millions of years. Above this thriving wetland rose several layers of vegetation. Towering conifers captured the highest sunlight. Broad-leafed deciduous trees occupied the middle canopy. Beneath them spread shrubs, young saplings, mosses, and water-loving plants that filled nearly every available space. Such layered forests create opportunities for countless ecological roles, allowing many species to share the same environment without competing for identical resources. Together, these fossil plants describe more than an unusual collection of trees. They demonstrate a climate warm enough to erase the familiar divisions between temperate and subtropical worlds, allowing botanical neighbors that the modern Earth no longer permits to grow side by side under the same northern sky. Few fossils carry as much weight as an alligator jaw. A single fragment of bone can reveal far more than the animal itself. It can describe the climate that sustained it, the rivers it hunted within, and the limits of temperature that surrounded its life. Among all the discoveries made in the Eocene Arctic, none speaks with greater clarity than the presence of crocodilian predators living year after year above the Arctic Circle. Modern alligators are governed by the temperature around them. Their bodies produce very little internal heat, leaving their muscles, digestion, and movement dependent upon the warmth of their surroundings. When conditions remain below about 40 degrees Fahrenheit for extended periods, they enter a state of greatly reduced activity. If warmth fails to return, survival becomes impossible. Their modern distribution follows that biological boundary with remarkable precision, ending wherever winter grows too severe. For paleontologists, this makes an alligator fossil something more than evidence of a reptile. It becomes evidence of climate itself. A cold-blooded predator cannot negotiate with freezing temperatures through behavior alone. It cannot migrate across thousands of miles every autumn and return each spring while maintaining breeding populations. If alligators lived in the Arctic, then the Arctic must have remained warm enough to support every stage of their lives, from hatchlings to fully grown adults. The species discovered on Ellesmere Island belongs to a crocodilian known as Allonathasuchus, an animal adapted to warm, swampy environments. Its fossilized jaw emerged during the field expedition, led by Mary Dawson in 1975. The discovery immediately challenged long-accepted assumptions about Arctic history because the fossil was unmistakable. No known process could place the jaw there except the existence of a climate suitable for a resident crocodilian population. Additional discoveries strengthened that conclusion. Crocodilian fossils later appeared on Banks Island, extending their confirmed northern range roughly 680 miles farther west across the Canadian Arctic. Such a broad distribution removed any lingering suggestion that the Ellesmere specimen represented an isolated accident. These reptiles occupied an extensive northern landscape, living across interconnected wetlands instead of surviving within a single unusual refuge. Chemical studies of associated fossils provided another important piece of evidence. Animals living permanently within one region preserve local environmental signals in their teeth and bones as they grow. Those signatures indicate that these crocodilians remained in the Arctic throughout the year. They were not seasonal visitors, escaping colder months elsewhere. Their lives unfolded beside the same rivers through every cycle of uninterrupted daylight and prolonged winter darkness. Those waterways suited their hunting strategy perfectly. Alligators spend much of their time waiting with extraordinary patience, exposing little more than eyes and nostrils above the water. When prey approaches, explosive acceleration replaces stillness within a fraction of a second. Warm channels winding through wetlands offered countless places where fish, turtles, mammals, and birds gathered to drink or cross, creating ideal conditions for ambush predators that relied upon surprise instead of pursuit. The alligator, therefore, became the foundation upon which the entire Arctic rainforest could be understood. Accepting its presence required accepting a climate capable of sustaining it. Accepting that climate meant accepting forests, wetlands, and a thriving northern ecosystem unlike anything alive today. Remarkable though these reptiles were, the waterways they occupied still held other predators whose stories reached even farther beyond ordinary expectation. One remarkable fossil can change a scientific idea. An entire community can transform it forever. As researchers continued uncovering specimens from Ellesmere Island after the discoveries of the 1970s, the Arctic rainforest became increasingly difficult to imagine through modern experience. Each excavation added another familiar tropical resident to a place where none seemed possible, until the collection resembled a living ecosystem transported thousands of miles north of its expected home. Among the largest herbivores were giant tortoises, carrying heavy shells through marshes and forest clearings with deliberate, unhurried movement. Their closest living relatives survive today on islands such as the Galapagos and the Seychelles, where warm climates remain stable throughout the year. Their presence in the Eocene Arctic provides another independent measure of temperature. Like the crocodilians, these reptiles depended upon conditions that never descended into prolonged, life-threatening cold. Waterways supported an equally rich assembly of turtles. Fossils representing several freshwater and semi-aquatic species have been recovered from river and lake deposits across the Ellesmere formations. They occupied ecological roles much like turtles living today in the southeastern United States, feeding on aquatic vegetation, invertebrates, and small animals while moving easily between ponds, channels, and flooded wetlands. Their shells appear repeatedly within sediments that once formed the floor of this extensive northern marshland. Larger predators also moved through the vegetation. Vertebrae belonging to members of the boa family reveal the presence of substantial constricting snakes related to modern boas and pythons. These reptiles hunted without venom, relying instead upon concealment and muscular strength. Hidden among roots, fallen logs, and dense undergrowth, they could overpower surprisingly large prey before swallowing it whole. Their fossils appear across the region, showing that these hunters formed an established part of the ecosystem rather than isolated curiosities. Perhaps the most unexpected mammals were the flying lemurs, also known as colugos. Despite their common name, they are neither true lemurs nor capable of powered flight. A broad membrane stretching between their limbs allowed them to glide from tree to tree with remarkable efficiency. Today, their relatives inhabit tropical forests in Southeast Asia. Finding their fossils above the Arctic Circle demonstrates that the northern canopy once supported an arboreal community far richer than anyone had imagined before these discoveries. The forest floor also sustained tapir relatives, sturdy browsing mammals with deep bodies and flexible feeding habits. Weighing several hundred pounds, they wandered through wet vegetation, consuming leaves, shoots, and aquatic plants. Their size placed them among the dominant herbivores of the middle layers of the forest, shaping vegetation through constant browsing while providing prey for the largest predators, occupying rivers and dense cover. Bird life flourished alongside mammals and reptiles. Fossils of Presbyornis, a graceful water bird related to modern ducks and geese, have been recovered from Ellesmere deposits. These remains represent the oldest known bird fossils from the age of mammals anywhere in the Arctic. Shallow lakes and slow channels likely offered ideal feeding grounds, where these birds filtered small aquatic organisms from the water. Early members of the Brontothere family also lived within this northern landscape. Although their descendants would later grow into massive rhinoceros-sized mammals farther south, these earlier forms already occupied the rainforest, adding another layer to its growing diversity. Taken together, the fossils reveal at least 25 mammal genera from a single Arctic island. Such abundance belongs to a complete ecosystem, one filled with browsers, gliders, swimmers, hunters, scavengers, and countless smaller creatures whose lives intertwined beneath a forest canopy, unlike any that exists on Earth today. Among the towering trees and winding wetlands lived a mammal whose appearance seemed borrowed from several different animals at once. It carried the broad body of a hippopotamus, the browsing habits of a large herbivore, and a head crowned with heavy jaws, built for crushing vegetation. Paleontologists know it as Coryphodon, a name meaning peaked tooth, one of the earliest giant browsing mammals to flourish after the disappearance of the non-avian dinosaurs. Coryphodon belonged to an extinct group known as the pantodonts, among the first mammals to reach truly impressive size after the age of dinosaurs ended. Fully grown individuals measured about 8.2 feet in length and stood roughly 3.3 feet at the shoulder. The largest approached 1,100 pounds, making Coryphodon the greatest land mammal of the early Eocene. Within the Arctic rainforest, it occupied a role much like that later filled by elephants and other ecosystems, shaping vegetation through constant feeding and movement. Its body reflected a life closely connected to water. Short, sturdy legs supported a barrel-shaped frame that moved comfortably through marshes and shallow channels. Like modern hippopotamuses in African rivers, Coryphodon likely spent much of its day among wetlands, where aquatic plants, soft vegetation, and muddy banks offered abundant food. Its broad feet distributed weight across saturated ground, allowing the animal to wander through environments that would challenge heavier creatures with narrower limbs. Its most surprising feature remained hidden inside the skull. Despite its enormous body, the brain weighed only about 3.2 ounces, giving Coryphodon one of the smallest brain-to-body proportions ever measured in any known mammal. A creature heavier than many modern automobiles carried a brain weighing less than a baseball. By ordinary expectations, such anatomy might suggest a poorly equipped survivor. The fossil record tells a remarkably different story. Coryphodon became one of the most successful mammals of its age. Fossils have been discovered across North America, Europe, Mongolia, and China, revealing a geographic distribution spanning much of the northern hemisphere. Such an extensive range reflects a lineage capable of thriving under many local conditions while maintaining stable populations across continents connected by the warm climates of the early Eocene. Its greatest adaptation emerged only after scientists examined the chemistry locked within fossil teeth. As each tooth formed, thin layers of enamel preserved traces of the foods consumed during that stage of life. Carbon isotope analysis revealed an extraordinary seasonal pattern. During months filled with continuous daylight, Coryphodon browsed flowering plants, aquatic vegetation, and fallen fruit scattered across the forest floor. When the long darkness returned, its diet changed almost completely. Pine needles, dead leaves, and fungi became the primary sources of nourishment until sunlight returned. Those seasonal shifts remain preserved within microscopic growth layers, each recording a chapter of the animal's life as clearly as rings preserved within a tree trunk. Tooth chemistry became a biological diary, revealing choices made across changing seasons more than 50 million years ago. Coryphodon endured, because it responded to the Arctic calendar with remarkable flexibility. The same individual became one kind of browser beneath uninterrupted summer daylight and another during the prolonged northern darkness, allowing one of the earliest giant mammals to prosper within a forest, unlike any living landscape on Earth. Few animals have carried a reputation as misleading as Gastornis. Its towering frame, heavy skull, and immense hooked beak seemed to announce a life devoted to hunting. For more than a century, artists, museums, and textbooks embraced that image with confidence. The fossil evidence appeared to describe an enormous predator striding through the forests of the early Eocene. Only much later did the bones themselves reveal a very different story. Gastornis was named in honor of Gaston Planté, whose discoveries helped introduce the animal to science. It lived from roughly 56 million until about 40 million years ago, leaving fossils across Europe, Asia, and North America, including the forests of Ellesmere Island. Standing about 6 feet tall and weighing several hundred pounds, it ranked among the largest birds of its age. Strong legs supported a broad body that could move steadily through dense vegetation, while an oversized head carried a deep, powerful beak unlike that of any living bird. Those features encouraged an interpretation that seemed perfectly reasonable. Paleontologists imagined Gastornis stalking small mammals through the undergrowth, seizing prey with tremendous force before crushing bones beneath its massive bill. Early horses such as Eohippus often appeared fleeing from the giant bird in museum murals and scientific illustrations. Generation after generation accepted the same picture. The nickname terror bird became firmly attached, even though the true South American terror birds belong to an entirely different branch of avian evolution. The confidence surrounding that image endured for nearly 150 years. Then a new analytical technique shifted attention away from appearances and toward chemistry. During 2013, researchers from the University of Bonn and the Max Planck Institute examined fossil bones using calcium isotope analysis. As calcium moves through a food web, lighter isotopes become concentrated in predictable ways. Herbivores and carnivores leave distinct chemical signatures behind, allowing diet to be reconstructed long after muscles and organs have disappeared. Gastornis delivered a result that surprised nearly everyone. Its calcium isotope pattern matched browsing animals rather than predators. The enormous bird had not occupied the top of the food chain by hunting flesh. Instead, it fed primarily on plant material. The evidence proved consistent across the specimens examined, replacing decades of confident interpretation with a simpler conclusion grounded in measurable chemistry. Its formidable beak suddenly acquired a different purpose. Instead of gripping struggling prey, it likely excelled at crushing hard seeds, splitting thick-shelled nuts, breaking woody stems, and processing dense vegetation scattered across the forest floor. Powerful jaw muscles still mattered, though their strength served a menu of resilient plant tissues instead of meat. Gastornis remained an imposing presence, though its daily routine probably involved deliberate foraging beneath towering trees instead of dramatic pursuits. Within the Arctic rainforest, appearances concealed reality in unexpected ways. The tallest bird in the ecosystem looked every bit the fearsome hunter imagined by generations of artists, while genuine danger waited elsewhere among the waterways, where crocodilians disappeared beneath the surface before striking. Gastornis reminds paleontology that anatomy offers valuable clues but rarely tells the complete story. Fossils preserve shape with remarkable fidelity, Yet the chemistry locked inside those same bones can overturn assumptions that once seemed beyond dispute, revealing a living world far richer and more surprising than first impressions ever suggested. Danger in the Eocene Arctic rarely announced itself. The broad channels winding through the forests appeared calm from above, their surfaces broken only by drifting leaves, floating branches, and reflections of towering trees. Beneath that appearance, an entire community of predators waited with remarkable efficiency. The rainforest, stretching across Ellesmere Island, supported hunters whose methods remain among the most successful ever shaped by evolution, transforming every river, swamp, and flooded woodland into contested ground. The lowlands formed an immense network of wetlands, connected by slow rivers, shallow lakes, marshes, and seasonally flooded forests. Water linked nearly every corner of the ecosystem, allowing predators to travel through habitats that herbivores visited each day for drinking, feeding, or crossing between patches of vegetation. These waterways did more than nourish the forest. They served as hunting corridors where concealment came naturally and hesitation often proved costly. Crocodilians ruled these aquatic passages through a strategy refined across immense spans of evolutionary time. Their bodies remained almost completely submerged, while eyes and nostrils rested above the surface, revealing almost nothing of the powerful animal below. Thick armor protected them from injury. Muscular tails delivered explosive bursts of speed, and jaws closed with tremendous force once prey entered reach. Instead of pursuing victims over great distances, they depended upon timing measured with extraordinary precision. Long periods of waiting could end within a fraction of a second as an unsuspecting animal approached the shoreline. Evidence from Ellesmere demonstrates that these reptiles represented stable populations rather than isolated visitors carried north by unusual circumstances. Fossils belonging to multiple crocodilian species have been recovered from the Arctic deposits, indicating breeding communities that occupied these waterways through countless generations. Such persistence could occur only because the surrounding climate remained warm enough to support every stage of their life cycle, from nesting to adulthood, across millions of years. The forests also sheltered another kind of ambush hunter. Large members of the Boyd family moved through dense vegetation with an entirely different approach. They carried no venom. Success depended instead upon concealment, rapid strikes, and overwhelming strength. Once their bodies wrapped around struggling prey, each breath tightened the coils further until movement ceased. Flexible jaws then allowed meals much larger than the width of the head to pass gradually into the body. Vertebrae recovered from Ellesmere reveal snakes substantial enough to overpower many of the medium-sized mammals sharing the rainforest. Far to the south, another reptile illustrated how profoundly the Eocene climate influenced cold-blooded predators. Titanoboa lived about 58 million years ago in tropical South America, reaching nearly 42 feet in length and weighing close to 2,500 pounds. It never inhabited the Arctic, yet its existence demonstrates the biological opportunities created by extraordinary planetary warmth. Across widely separated regions, reptiles achieved dimensions difficult to imagine under modern climatic conditions. Animals living within the Arctic rainforest faced choices familiar to inhabitants of present-day wetlands, where large reptiles remain dominant. Every crossing carried uncertainty. Every muddy bank concealed possibility. Fish, turtles, water birds, browsing mammals, insects, and countless smaller creatures form the layers of a complete food web, all supporting predators at its summit. The title of the deadliest rainforest belongs not to one remarkable species, but to an ecosystem where nearly every stretch of water functioned as a carefully prepared ambush, shaped by millions of years of patient evolution. Maps of the modern world encourage the impression that continents have always stood apart, divided by broad oceans that prevent most land animals from crossing between them. During the early Eocene, that familiar geography had not yet fully emerged. Across the far north, the landscape formed a chain of connected passages where forests stretched across regions now separated by icy seas. The Arctic did not stand at the edge of the inhabited world. It formed one of its busiest biological crossroads. The North Atlantic remained much narrower than it is today, while the Norwegian Greenland Sea had not yet deepened into the broad marine barrier that now separates continents. Between North America and Europe, stretches of land appeared and disappeared as sea levels shifted. Paleontologists refer to this northern connection as the Thulian Land Bridge, named after Thule, the ancient Greek name for the distant northern world. During favorable intervals, forests extended across this route, creating a continuous corridor for plants and animals moving between continents. Its influence appears clearly within the fossil record. Mammal families that seem to emerge almost simultaneously in both North America and Europe shortly after the Paleocene-Eocene thermal maximum are difficult to explain unless a practical route connected the continents. The distribution was not random. Species dispersed with surprising speed, following expanding forests into territories that had become newly accessible. Bones preserved thousands of miles apart record movements that unfolded across a connected northern landscape rather than isolated landmasses. Another pathway extended across the opposite side of the Arctic. The Bering Land Bridge linked North America with Asia, providing an additional route through the northern forests. Long after the Eocene ended, anatomically modern humans would eventually pass through this same region while entering the Americas between roughly 15,000 and 20,000 years ago. During the early Eocene, however, the travelers were mammals, reptiles, birds, and countless smaller creatures expanding alongside favorable climates and abundant vegetation. Together, these northern passages transformed the Arctic into a corridor joining three continents. An animal beginning its journey in what is now Alaska could continue across connected forests into Europe, while another population might spread westward into Asia without encountering the immense marine barriers familiar today. The rainforest did more than shelter life. It stitched distant ecosystems together, allowing evolution to proceed across an enormous, connected landscape. Coryphodon illustrates this remarkable geography with unusual clarity. Fossils belonging to the same widespread browsing mammal have been recovered from Ellesmere Island, the central regions of North America, Europe, Mongolia, and China. Such an extensive distribution becomes understandable once the northern land bridges are restored to the map. Rather than isolated populations appearing independently, these animals expanded gradually through continuous habitat, following wetlands and forests across the high latitudes. Other discoveries reinforce the same pattern. Crocodilian fossils recovered from Banks Island, roughly 1,100 miles west of Ellesmere, demonstrate that warm, adapted reptiles spread along these northern waterways as suitable climates persisted. Flying lemurs, early primates, tapir relatives, and additional mammal groups appear in comparable forms across multiple continents during the early Eocene. Their shared history becomes coherent only when the Arctic is viewed as a connected landscape instead of a remote frontier. The frozen ocean and polar desert, visible today, conceal the traces of that former network. During the height of the Eocene greenhouse world, the Arctic rainforest did not represent an isolated sanctuary where unusual species survived apart from everything else. It functioned as the great northern highway of its age, carrying forests, animals, and evolutionary opportunity between continents that remained linked beneath the same broad canopy. The shoreline of any world reveals its climate as clearly as its forests or mountains. During the early Eocene, the boundaries between land and sea followed an entirely different design. The familiar outlines traced across modern globes had not yet taken shape. Oceans reached far across continental margins, while coastlines rested in places that no longer exist except within layers of ancient rock. The reason was straightforward. Earth carried no permanent polar ice sheets, no enduring continental glaciers, and no lasting snowfields capable of storing immense volumes of frozen water. The Greenland ice sheet, which alone contains enough frozen water to raise global sea levels by roughly 24 feet, had not formed. Antarctica also remained free of the colossal ice sheet that today holds enough water to increase sea levels by about 190 feet. Water now imprisoned in ice, instead, filled the oceans. As a result, global sea levels stood roughly 200 to 330 feet higher than those of the present day. Such a rise reshaped every continent. Coastal plains disappeared beneath shallow seas, while inland basins became broad marine embayments. Maps familiar to modern eyes would have offered little guidance to a traveler standing upon an Eocene shore, because the edges of nearly every landmass had shifted. Across North America, the Gulf of Mexico reached much farther into the continent. Areas now occupied by extensive coastal plains lay beneath warm seawater, while large portions of the modern Gulf Coast, Florida, and stretches of the eastern seaboard rested below the waves. Rivers entered the sea along coastlines positioned far inland from their present locations, altering habitats over thousands of miles and creating broad regions where marine and freshwater environments blended together. Europe carried a different appearance as well. Much of Western Europe resembled an archipelago, with islands divided by shallow inland seas. Britain remained separated from mainland Europe, although the waterway between them bore little resemblance to the modern English Channel. The marine passages were broader, their coastlines more irregular, and their surrounding lowlands submerged beneath water that reflected the warmth of the greenhouse world. Even the Arctic Ocean defied modern expectation. Sediments deposited during the height of the Paleocene-Eocene Thermal Maximum preserve evidence that surface waters approached approximately 73 degrees Fahrenheit. At the highest latitudes on Earth, the ocean possessed temperatures comparable to those found in parts of the modern Caribbean. Those warm northern seas bordered the forests already rooted across Ellesmere, linking marine and terrestrial ecosystems unlike any combination found today. The consequences extended across every continent. Cities that now anchor global civilization, including New York, London, Shanghai, Miami, and Mumbai, occupy coastlines created by the later growth of great ice sheets. In the Eocene world, many of those locations would have rested beneath shallow ocean water or along entirely different shores. Human geography depends upon an icehouse planet that arrived millions of years after these forests flourished. The rainforest on Ellesmere belonged to that vanished arrangement. Its rivers, nearby seas, and surrounding continents occupied positions shaped by an Earth without permanent polar ice. The coastlines supporting modern civilization are products of a much younger climate. During the Eocene, the planet followed another map entirely, one that remained stable for millions of years before ice drew the oceans back and sketched the familiar world of today. Among the branches of this northern forest lived another surprise, one measured not by size or strength, but by lineage. Small mammals with grasping hands and forward-facing eyes reached a latitude where their relatives have never been found again. Their fossils record the farthest journey any known primate relative has ever completed, carrying a family of warm forest animals into a landscape balanced between abundant life and half a year without sunlight. In 2023, a study published in the journal Public Library of Science 1 described two previously unknown species of Ignacius, members of a broader group known as Primatomorpha. Their remains came from Ellesmere Island at roughly 77 degrees north latitude. The announcement drew immediate attention because these creatures represent the northernmost primate relatives ever documented anywhere in the fossil record. Even distant members of the primate family are typically associated with forests rich in light, fruit, and year-round biological productivity. Their arrival was no accident of chance. The timing aligns closely with the early Eocene climatic optimum, the warmest interval of the Eocene, spanning roughly 53 million to 49 million years ago. As warmth expanded toward the poles, forests stretched with it, opening ecological pathways that had never before existed. Ancestors of these small mammals gradually followed those living corridors northward until they reached a region that had become inviting in temperature while remaining governed by the same polar rhythm of light and darkness. Crossing that threshold placed them inside an environment unlike any occupied by their southern relatives. Summer offered abundant opportunity, with flowering plants, insects, seeds, and fruit supporting a diverse woodland community. Then the yearly disappearance of the sun transformed the forest. Food that depended upon fresh growth became scarce, while durable plant resources remained available long after leaves had fallen and blossoms had vanished. Survival favored individuals capable of exploiting those tougher reserves. Their skeletons preserve evidence of that shift. Compared with related species farther south, the Ellesmere forms possessed stronger jaws, thicker tooth enamel, broader chewing surfaces, and distinctive wear patterns etched across their teeth. These were measurable anatomical differences rather than minor variation. Paleontologists propose that the heavier dental equipment evolved because winter forced these animals to rely increasingly upon hard seeds, resilient nuts, and other durable foods capable of lasting through months without new plant growth or plentiful insects. The remarkable detail is that warmth alone did not shape these mammals. Their bodies responded to darkness. Evolution altered their feeding equipment because each annual cycle demanded a strategy suited to a forest that entered prolonged biological dormancy, while temperatures remained comparatively mild. Every generation inherited small advantages that gradually accumulated into a form distinct from its lower latitude relatives. Only two species are presently known, suggesting a single successful colonization followed by adaptation within the Arctic itself. Their ancestors pursued expanding forests toward the highest latitudes ever reached by their lineage. Once established, retreat was not their only option. Natural selection reshaped them for the place they had entered, preserving populations that could withstand conditions unlike any experienced elsewhere. Their fossils leave behind a modest but profound message. Even among close relatives of the primate family, evolution found a path through 6 months of darkness. The Arctic did not merely receive these travelers. It transformed them, one generation at a time, until their teeth carried the lasting imprint of a world where warmth and polar night existed together. Weather shaped this forest as profoundly as the creatures that wandered beneath its canopy. The word rainforest often suggests gentle showers drifting through warm trees from morning until evening. The Arctic forest followed a far more dramatic rhythm. Its seasons were driven by the movement of light across the planet, producing cycles of flooding, relentless plant growth, and long intervals of darkness that have no true counterpart in the modern world. Evidence for this pattern survives in the leaves themselves. Research published in Earth and Planetary Science Letters examined fossil leaf physiognomy, the shapes, edges, and vein networks preserved within ancient plants. Those features reveal the conditions under which the leaves developed, allowing scientists to reconstruct rainfall across the Eocene Arctic with surprising precision. The resulting picture shows precipitation arriving unevenly through the year instead of falling at a constant pace. Much of the annual rainfall came during concentrated wet seasons, forming a monsoonal climate rather than one defined by frequent, gentle showers. The atmosphere gathered moisture over time before releasing it in heavy bursts. Rivers expanded beyond their usual banks, wetlands spread across the lowlands, and standing water connected forests, lakes, and winding channels into one broad aquatic landscape that shifted with each season of abundant rain. The engine behind this cycle was not changing temperature, but changing daylight. During the Arctic summer, the sun remained above the horizon for months without setting. Continuous illumination poured energy into the landscape every hour of every day. Warm surface waters of the Arctic Ocean released increasing amounts of moisture into the air through evaporation. Moisture-laden clouds formed, drifted inland, and eventually returned their water to the forest in powerful seasonal downpours. Plants responded with astonishing speed. Photosynthesis continued around the clock because darkness never interrupted it. Trees extended new branches, broad leaves spread across the canopy, and wetland vegetation flourished in conditions that few temperate forests could ever match. Growth accumulated hour after hour without the nightly pause, familiar across lower latitudes. Every layer of the forest took advantage of the prolonged light, creating extraordinary biological productivity within a relatively brief part of the year. Animal life adjusted as well. Abundant water and flourishing vegetation attracted herbivores toward rivers, ponds, and flooded clearings. Predators followed those gatherings, finding reliable opportunities wherever travel routes narrowed along swamp margins or shallow channels. The busiest season in the forest coincided with the brightest months, when life concentrated around the expanding waterways that threaded through the landscape. Flooding became a recurring force rather than an occasional disaster. Winter snowfall accumulated across higher elevations before melting as warmer conditions returned, adding fresh water to rivers already swollen by monsoonal rains. Sudden inundation buried plants and animals beneath layers of mud and sediment. Many of the fossils recovered from Ellesmere occur within ancient riverbeds and lake deposits because rapid burial protected bones, leaves, and wood before decay could erase them. Then the rhythm reversed. Light disappeared, temperatures approached the freezing point, and biological activity slowed across the forest. Nearly 30 degrees Fahrenheit separated the brightest part of the year from the darkest. There was little transition between those extremes. Explosive summers yielded to prolonged polar night, yet the forest endured both. No living ecosystem combines continuous summer daylight, monsoonal rainfall, prolonged winter darkness, and year-round rainforest conditions. The weather itself belonged to a chapter of Earth that has never returned. Some discoveries begin with a bold prediction. Others emerge from a patient search through rocks that have waited millions of years to speak. The Arctic rainforest belonged to the second kind. Its return to science did not begin with certainty. It began when a small fragment of bone appeared from a hillside on Ellesmere Island and refused to fit the world. Scientists believed they understood. Before 1975, the prevailing picture of Arctic history was remarkably straightforward. The far north was widely regarded as a region that had always belonged to cold climates. Ice sheets, frozen ground, and barren polar landscapes were treated as enduring features of the planet, stretching deep into geological time. Earlier warm intervals were recognized in broad terms, yet few imagined that the high Arctic itself had once supported forests inhabited by animals requiring mild conditions throughout the year. Mary Dawson of the Carnegie Museum of Natural History organized an expedition to Ellesmere because geological mapping suggested that exposed rock layers dated to the Eocene and might preserve mammal fossils. The goal was ambitious but conventional. The team expected fragments of extinct mammals that could help clarify evolutionary history. Nothing in their plans anticipated the fossil that would emerge from those rocks. Among the discoveries lay the unmistakable remains of an alligator jaw. Its shape, tooth sockets, and structural features left no realistic room for another interpretation. The fossil belonged to an animal whose biology demanded sustained warmth. Either an alligator had once lived within the Arctic Circle, or every clue surrounding the specimen had somehow become misleading at once. The surrounding geology made that second possibility increasingly difficult to defend. Initial reactions reflected genuine scientific caution mixed with disbelief. An alligator living near 79 degrees north latitude conflicted with accepted ideas about Arctic history. If the fossil was authentic and correctly dated, then the established picture required revision. The question was no longer whether the evidence fit existing theory. Existing theory had to account for evidence that could not be ignored. Subsequent field seasons transformed a surprising fossil into an entirely new understanding of the ancient Arctic. Expeditions returned summer after summer, working within one of the most isolated and demanding research environments on Earth. Each season recovered additional mammals, reptiles, birds, plants, and chemical evidence preserved within bones, teeth, wood, leaves, and sediments. Every discovery reinforced the same conclusion while filling another gap in an expanding picture assembled piece by piece across decades. Another remarkable site strengthened that growing case. At Strathcona Fjord, researchers encountered permineralized tree stumps, still standing upright, their roots preserved where the living forest had once grown. They projected directly from coal-bearing rock, occupying the same positions in which they had ended their lives roughly 52 million years ago. The forest had not been transported there. It had grown there. Even the coal itself carried unmistakable meaning. Coal forms through the accumulation and burial of abundant plant material over long intervals. Thick coal seams crossing Arctic bedrock therefore recorded prolonged forest growth long before fossil animals entered the story. The evidence had rested within the landscape all along, awaiting the questions capable of revealing its significance. The jaw recovered in 1975 did far more than identify one unexpected reptile. It overturned a deeply rooted assumption about the Arctic itself. What appeared to be an immutable frozen wilderness proved instead to be only the latest chapter in a history far richer, warmer, and more surprising than science had once imagined. A fossil tooth can rest unnoticed in the palm of a hand no larger than a thumbnail, yet it carries a history beyond anything visible on its surface. Long after flesh has vanished and many bones have fractured beneath millions of years of Arctic freezing and thawing, tooth enamel often remains. Among the discoveries scattered across Ellesmere Island, these durable fragments have become some of the richest sources of evidence, preserving details of lives that unfolded roughly 52 million years ago. Teeth endure because enamel is the hardest biological material produced by vertebrate animals. While surrounding skeletons may break apart or dissolve, enamel protects a chemical record formed layer by layer during growth. Each layer captures conditions existing at that precise stage of life. Instead of relying only upon rocks or sediments, researchers can examine the animals themselves, reading information preserved inside their own tissues. One of the most valuable clues comes from oxygen isotopes, atoms of oxygen carrying different numbers of neutrons and therefore slightly different masses. As enamel develops, oxygen from drinking water becomes locked into its mineral structure. The balance between heavier and lighter oxygen isotopes changes according to water temperature. Warmer conditions leave one chemical pattern, cooler conditions another. Millions of years later, that pattern remains preserved inside the tooth, allowing scientists to estimate the temperatures experienced while the enamel formed. Confidence grew even stronger when researchers from the University of Colorado analyzed teeth belonging to three different animals recovered from the same Arctic ecosystem. They examined a Coryphodon, a tapir relative, and a Brontothere independently. Each species produced closely matching temperature signals despite their differing lifestyles. Agreement across unrelated mammals demonstrated that the measurements reflected the surrounding climate rather than the biology of one particular animal. Those chemical records indicated summers reaching roughly 68 degrees Fahrenheit, while winters settled between about 32 and 38 degrees Fahrenheit, values preserved within living creatures instead of stone. Carbon isotopes reveal another layer of the story. Carbon exists naturally in forms with different atomic masses, and plants incorporate those forms in subtly different proportions. As herbivores consume leaves, aquatic vegetation, fruits, fungi, or other foods, those dietary signatures become recorded within growing enamel. Variations across successive growth layers allow scientists to reconstruct seasonal feeding habits, showing how individual animals adjusted their diets as changing conditions reshaped the forest around them. Calcium isotopes answer an entirely different question. Lighter calcium becomes progressively concentrated higher in the food chain as predators consume prey. When researchers examined Gastornis using this method in 2013, the bones displayed the unmistakable calcium pattern of a plant eater. One chemical measurement overturned more than a century of confident interpretation, revealing that its enormous beak served vegetation instead of flesh. Strontium isotopes add one final dimension. Because bedrock differs from place to place, local water carries distinctive strontium signatures. Those signatures enter plants, then animals, before becoming sealed inside enamel. A tooth, therefore, preserves the chemical identity of the landscape where it formed, allowing scientists to recognize whether an individual remained in one region or traveled across distant environments during its lifetime. These remarkable fossils preserve far more than shape or size. Every tooth functions as a mineral archive, recording climate, diet, geography, and behavior with extraordinary fidelity. Read through the precision of modern mass spectrometers. Those tiny fragments become written biographies, composed by living animals and carried intact across 52 million years until the Arctic was finally ready to tell its story. Nothing announced the ending. No single season marked the turning point, and no horizon revealed that the world had begun to change. The forests still spread across the northern landscape, rivers still wandered through broad lowlands, and familiar animals continued their daily rhythms. Even so, the conditions that had sustained this remarkable place were already shifting in ways too gradual for any living creature to perceive. Following the peak of the early Eocene climatic optimum, roughly between 53 and 49 million years ago, atmospheric carbon dioxide entered a prolonged decline. Several natural processes worked together across immense spans of time. Volcanic activity diminished, releasing less carbon dioxide into the atmosphere. Exposed mountain ranges weathered under rainfall, drawing additional carbon dioxide from the air through chemical reactions. At the same time, increasing amounts of carbon became buried within expanding layers of ocean sediment, locking it away for millions of years beneath the sea floor. As atmospheric carbon dioxide slowly decreased, the greenhouse effect weakened step by step. The transformation unfolded with extraordinary patience. Any single generation would have experienced a landscape appearing much the same as that inherited from its parents. Across thousands of generations, however, small changes accumulated until they reshaped entire ecosystems. Average global temperatures drifted downward by several degrees Fahrenheit during the Middle and Late Eocene, progressing at a pace measured in geological time instead of ordinary seasons. The Arctic responded with particular sensitivity because its warmth depended upon keeping polar cold from gaining strength. Even modest cooling lengthened winter conditions and shortened the growing season. Frost returned after an absence lasting roughly 20 million years. Plants that had flourished beneath continuous summer daylight now faced colder, dormant months, and each passing age narrowed the span available for new growth before darkness returned once again. The living community answered by following the warmth toward lower latitudes. This migration unfolded gradually, without dramatic boundaries separating one age from the next. Fossil pollen preserves the sequence with remarkable clarity. Palm species disappeared from Arctic sediments before magnolias vanished. Magnolias retreated before the cypresses. Cypresses persisted longer than the towering redwoods, yet even they eventually yielded as the climate continued its measured descent. Each disappearance marked another step in the long withdrawal of a forest that had once reached the edge of the polar sea. The alligators also faded from the northern record. Their fossils become increasingly scarce before disappearing altogether, leaving no sudden boundary, only absence replacing presence. Their bodies had always depended upon winters remaining mild enough for survival. As colder seasons strengthened, that balance slipped beyond their limits. No descendant evolved the ability to endure the increasingly severe Arctic cold, and the lineage abandoned the region completely, following climates that still resembled the world where it had first prospered. Gradually, the forest opened. Wetlands contracted into smaller pockets, while streams and lakes spent longer portions of each year under ice. Every subtle shift encouraged another, altering habitats that countless species had occupied together for millions of years. The last Arctic alligator disappeared without witnessing the full transformation surrounding it. Long after that final life ended, the cooling continued, carrying the northern world toward an identity entirely different from the rainforest that had once flourished beneath its changing sky. The ending arrived when the planet crossed a boundary from which there was no return. For millions of years, the Arctic rainforest had adjusted to a climate that cooled with immense patience, surrendering species one after another as warmth withdrew toward lower latitudes. Then, roughly 34 million years ago, Earth entered a transformation so profound that geologists still recognize it as the greatest climatic turning point of the entire Cenozoic era. By the time of the Eocene-Oligocene transition, atmospheric carbon dioxide had declined far below the extraordinary concentrations that once sustained forests at the top of the world. Antarctica reached a threshold where winter snowfall no longer disappeared completely during summer. For the first time in tens of millions of years, snow survived from one season into the next. That persistence changed everything because fresh snow reflected far more sunlight back into space than dark rock or open ground. The effect strengthened itself with remarkable efficiency. Expanding ice reflected additional sunlight, reducing the amount of heat absorbed by the surface. Cooler conditions encouraged even more snow to remain through successive summers. Each growing layer of ice reinforced the next, establishing a powerful climatic feedback that carried the continent toward a completely different state. Once this cycle gathered momentum, it continued until Antarctica became covered by an immense permanent ice sheet. Geologists estimate that the East Antarctic ice sheet formed within roughly 100,000 to 200,000 years, astonishingly rapid on the timescale of Earth's history. Average global temperatures fell by approximately 7 degrees Fahrenheit as the expanding ice transformed atmospheric circulation and planetary energy balance. Oceans responded alongside the atmosphere, redistributing heat in patterns that increasingly resembled those operating across the modern world. As enormous quantities of water became locked inside continental ice, sea levels declined across the globe. Coastlines advanced seaward as shallow inland seas retreated from continental interiors. Marine passages narrowed or disappeared, exposing new stretches of land while altering ocean currents that had once transported warmth across the planet. The geography supporting the greenhouse world steadily reorganized into the foundations of the cooler Earth that would follow. Evidence for this transition appears with striking clarity inside marine sediment recovered from widely separated oceans. Oxygen isotope ratios preserved within microscopic shells shift abruptly at this interval, recording the combined influence of colder seawater and expanding continental ice. The signal is so consistent that geologists can identify the onset of Antarctic glaciation from sediment cores collected thousands of miles apart, all preserving the same unmistakable planetary turning point. For the Arctic rainforest, this transformation unfolded as the final commitment to decline. The cooling itself had begun much earlier, yet enough warmth had lingered for remnants of the old ecosystem to endure. After Antarctica froze, the balance changed permanently. The greenhouse conditions required to support broad northern rainforests could no longer extend into polar latitudes. Every remaining refuge contracted farther south as familiar habitats dissolved into landscapes increasingly shaped by frost, shortening summers, and expanding seasonal ice. No single storm erased the forest, and no single generation witnessed its complete disappearance. The decisive moment lay in the freezing of a distant continent whose growing ice reshaped the entire planet. From that threshold forward, Earth entered an icehouse world that would continue for roughly 34 million years, carrying the Arctic toward the frozen identity that would one day conceal the memory of its vanished rainforest. The disappearance of the Arctic rainforest unfolded with extraordinary patience. No single catastrophe erased it, and no sudden boundary separated one living world from another. The forest yielded gradually, surrendering pieces of itself across millions of years as favorable climates slipped farther south. Each generation inherited a landscape only slightly altered from the last, while the accumulated changes slowly reshaped an entire continent. Among the earliest great losses was Coryphodon. By roughly 47 million years ago, this broad-bodied browser had vanished from the Arctic record, long before Antarctica entered its great freezing episode. Its life had been closely tied to extensive warm wetlands and abundant marsh vegetation. As cooling shortened growing seasons and transformed swamp habitats, the conditions supporting such a specialized animal steadily diminished. The lineage survived elsewhere for a time, yet its northern chapter ended as the environment drifted beyond the limits its long evolution had prepared it to endure. Gastornis remained somewhat longer. Unlike Coryphodon, its powerful beak allowed it to process an impressive variety of hard plant foods that persisted after softer fruits became less dependable. That flexibility provided valuable resilience while forests became more open and seasonal resources shifted. Even so, adaptation could not reverse the broader climatic trend. Around 40 million years ago, Gastornis also disappeared from the fossil record, leaving behind only scattered bones that would eventually correct centuries of misunderstanding about its true way of life. The crocodilians followed a different path. Their family continued thriving across warmer parts of the world by retreating with the climate instead of confronting increasingly severe northern winters. Fossils reveal their gradual withdrawal from Arctic waterways until they vanished completely from the region. No branch evolved the capacity to survive permanently within the cooling polar environment. Their northern history concluded through absence rather than replacement, while relatives endured in rivers and wetlands where warmth remained dependable. The forests themselves retreated in much the same manner. Swamp cypresses shifted southward alongside the climates that had long sustained them. Today, their descendants flourish within the bayous of Louisiana and the wetlands of Florida, occupying environments that echo aspects of the ancient Arctic lowlands. Towering redwoods withdrew toward the Pacific coast of California, with another surviving lineage persisting in China. Magnolias settled across the American South and Eastern Asia, while alders and birches became defining trees of cooler, temperate forests that replaced the vanished rainforest. These migrations were not global extinctions. Many of the organisms that once flourished near the polar sea still live today, separated from their Arctic ancestors by millions upon millions of generations. A swamp cypress rising from a modern southern marsh belongs to a lineage whose distant relatives once rooted themselves in soils now locked beneath snow, stone, and frozen ground. Their continued existence preserves a living connection to a landscape that otherwise seems impossible. What remained behind was gradually buried. Fallen trunks, leaves, roots, and countless other fragments accumulated within wetlands before becoming compressed beneath younger sediments. Pressure, mineral-rich water, and immense spans of time transformed that organic abundance into coal seams running through the bedrock of Ellesmere Island. The rainforest became stone without losing every trace of itself. Hidden beneath layers deposited during the succeeding icehouse world, its memory endured until patient hands uncovered a weathered jaw, opening the first page of a forgotten northern chapter that the rocks had safeguarded across 34 million years of cold. Every fossil begins with a journey across one of the least forgiving landscapes on the planet. The rainforest has long since vanished, yet the ground where it once flourished continues to welcome only a handful of visitors each year. Reaching Ellesmere Island demands careful planning, chartered aircraft, favorable weather, and patience, carrying researchers into a place where distance itself becomes part of the scientific work. The expedition usually begins from Resolute Bay in Nunavut, among the northernmost inhabited communities in Canada. Beyond that settlement, roads disappear and ordinary infrastructure fades away. Camps must be established with nearly everything required for weeks of work, because outside assistance cannot arrive quickly if conditions change. The brief field season lasts only about 3 to 6 weeks during summer, when winter snow has withdrawn enough to expose the rock and temperatures remain above freezing for long enough to make excavation possible. Ironically, that narrow interval is all that remains of a season which, during the Eocene, stretched across months of flourishing life. Outcrops containing fossils rarely surrender their contents easily. Bones, teeth, leaves, and wood rest within hardened layers that demand steady effort with hammers, chisels, and fine brushes. Permafrost protects these remains from rapid decay, yet the same frozen ground resists every attempt to free them. Each fragment is photographed, mapped, labeled, and documented before removal so that its exact position becomes part of the scientific record. A misplaced specimen could erase valuable clues about the environment that surrounded it millions of years earlier. Among every discovery, fossil teeth receive exceptional attention. Enamel is the hardest tissue produced by vertebrate animals, allowing teeth to endure repeated freezing, thawing, burial, and erosion that often destroy more delicate bones. Even then, many recovered specimens are incomplete or heavily worn. Distinguishing one species from another frequently depends upon details measured in fractions of an inch. Researchers rely upon scanning electron microscopy to examine microscopic wear patterns and surface structures invisible to the naked eye. Months of laboratory study may follow before a single fragment can be assigned confidently to its proper genus. The contrast between present and past feels almost impossible to ignore. Scientists wrapped in heavy Arctic clothing kneel over frozen ground while uncovering evidence of alligators, towering trees, and animals that thrived in warmth. The cold preserving those fossils belongs to the very climatic transformation that erased the ecosystem they now reconstruct. Every careful strike against the rock bridges two profoundly different versions of the same landscape. Some discoveries require remarkably little imagination. At Strathcona Fjord, upright tree stumps still emerge directly from ancient coal seams. Researchers can rest a gloved hand upon wood that rooted itself more than 52 million years ago, remaining exactly where the living tree once stood. Around those trunks stretches a landscape where no forest grows today, only exposed stone, frost-shaped ground, and open sky. Each summer adds another page to the record. New species continue to appear, chemical analyses become more refined, and earlier interpretations are tested against fresh evidence. Knowledge accumulates through persistence instead of sudden revelation. The Arctic rainforest survives because people continue returning to a place shaped by cold, searching patiently through rock until another fragment allows the vanished world to speak once more. Extinction often begins long before the final individual disappears. It starts when the world that shaped a species begins changing in ways that fall outside every adaptation written into its body. The animals of the Eocene Arctic did not vanish through failure or weakness. They reached the limits of traits that had served them well for millions of years, until the landscape that rewarded those traits no longer existed. Coryphodon stands among the clearest examples. Across the early Eocene, it spread through North America, Europe, and Asia, becoming one of the dominant large plant eaters of its age. Its broad diet, sturdy frame, and comfort in warm wetlands allowed it to flourish across immense distances. Success, however, does not guarantee permanence. Every feature that made Coryphodon effective belonged to an environment rich with swamps, abundant vegetation, and winters mild enough for its slow physiology. As cooling shortened growing seasons and wetlands retreated, those advantages gradually became burdens. The animal possessed no inherited pathway toward life in colder, drier habitats. The crocodilians followed a similar pattern. They were neither primitive nor poorly equipped compared with relatives living farther south. They belonged to the same enduring lineage, occupying the northern edge of a range made possible by extraordinary warmth. When that band of favorable climate shifted toward lower latitudes, the reptiles shifted with it. Their disappearance from Arctic rocks records a retreat instead of a dramatic collapse. The northern frontier emptied because the conditions supporting crocodilian life no longer remained. Again and again, the fossil record preserves this rhythm. Ecosystems often decline through gradual environmental change instead of sudden catastrophe. A slight shortening of the growing season, another season of colder winters, another reduction in suitable habitat, each alteration may seem modest on its own. Across thousands of generations, those changes accumulate until reproduction slows, populations fragment, and familiar communities dissolve into smaller pockets before disappearing from a region altogether. Evolution offers remarkable flexibility, yet it possesses no ability to anticipate future conditions. Natural selection can refine structures, behaviors, and physiology only from circumstances already present. A species exquisitely suited to one climate inevitably carries compromises that reduce success under another. Adaptation follows change, never precedes it. When environmental transformation unfolds more rapidly than populations can adjust, biological history becomes filled with absences where thriving communities once stood. The Arctic of today is inhabited by creatures shaped under entirely different circumstances. Polar bears, walruses, musk oxen, and Arctic foxes belong to a world governed by recurring ice ages. Their evolutionary stories unfolded during approximately the last 2.6 million years, after cold climates had become established across the high north. Polar bears themselves emerged from brown bear ancestors roughly 150,000 years ago, making them remarkably recent in geological time. Every aspect of their survival depends upon sea ice, frozen coastlines, and prey adapted to the same conditions. They possess no direct equivalent within the Eocene rainforest and no inherited experience of an ice-free Arctic. The vanished forest, therefore, offers no blueprint for the future. It reveals a broader principle written repeatedly across Earth's history. Living communities endure while the conditions that shaped them endure. When those conditions fade, even the most successful species must either follow the changing world, transform alongside it, or eventually pass into stone, leaving their story for another age to uncover. The rocks of Ellesmere Island are no longer read-only as records of vanished life. They have become reference points for understanding a future that has not yet fully unfolded. Paleoclimatologists describe places like this as deep time analogs, a technical term for an ancient climate that resembles a projected future closely enough to test and improve modern climate models. The comparison is not built upon imagination. It rests upon measurable evidence preserved across millions of years. Among all known greenhouse climates, the early Eocene climatic optimum provides the closest geological example of an Arctic without permanent polar ice. Fossils, sediment chemistry, fossil pollen, tree rings, and mineral signatures converge upon the same picture. High concentrations of atmospheric carbon dioxide sustained conditions warm enough for forests, wetlands, and animals normally associated with far lower latitudes. Because the evidence comes from many independent sources, Researchers use this interval as a benchmark for examining how Earth's climate system responds when greenhouse conditions become strong enough to reshape the poles. The scientists who reconstructed temperatures from fossil teeth on Ellesmere Island recognized this connection directly. In their published work, they noted that the findings carry implications for understanding future climate change as Arctic temperatures continue rising. Their research was not presented as a prediction of identical landscapes returning. Instead, it established physical boundaries for what the planet has already demonstrated it can sustain under elevated carbon dioxide. The Arctic has occupied the state before, making it part of Earth's documented history instead of theoretical possibility. One lesson appears repeatedly throughout both ancient evidence and modern observation. High northern latitudes respond more strongly than the global average when greenhouse warming intensifies. This pattern, known as polar amplification, shaped the Eocene Arctic and is unfolding again today. Instrumental records collected across recent decades show Arctic temperatures increasing roughly 2 to 4 times faster than the planetary average. Although the continents, ocean currents, and living communities differ from those of the Eocene, the underlying physics governing heat, transport, and feedbacks continues following familiar principles. Sea ice provides another example. Observations show that the minimum summer extent of Arctic sea ice has declined substantially during the satellite era. Climate projections, estimating when nearly ice-free summer conditions may occur, have gradually shifted toward earlier dates, as measured change has exceeded many previous expectations. At the same time, thawing permafrost is releasing methane and carbon dioxide that remained stored in frozen ground since the most recent ice ages. Those emissions create an additional warming influence, with chemical echoes of processes that researchers have proposed for ancient greenhouse episodes. Although the precise sequence of events remains an active area of investigation, even so, the Eocene offers no catalog of future Arctic wildlife. Polar bears, walruses, caribou, musk oxen, and Arctic foxes evolved within an ice-dominated world that developed long after the rainforest disappeared. They had not yet emerged when crocodilians moved through northern rivers and broadleaf forests reached the polar horizon. Their responses to ongoing environmental change cannot be read directly from Eocene fossils because their evolutionary histories began under entirely different conditions. The deeper lesson lies elsewhere. The geological record establishes the physical range of what Earth has already achieved. An Arctic without permanent ice, carrying forests and warmth far beyond their modern limits, belongs to reality preserved in stone. Those rocks describe the destination once reached. They cannot reveal how it feels to inhabit the passage between one world and another. A journey is shaped not only by where it ends, but also by the pace at which each step unfolds. The ancient greenhouse world emerged through changes that stretched across spans almost beyond imagination. Forests expanded, rivers shifted, and animals followed the warmth through generations beyond counting. The destination transformed the planet, yet the path allowed lifetime to respond as climates slowly rearranged themselves. The Paleocene-Eocene Thermal Maximum, the great warming episode that opened the way toward the rainforest world of the high Arctic, unfolded across roughly 10,000 to 20,000 years. By geological standards, this was exceptionally rapid, yet every century represented only a small fraction of the overall transition. Trees dispersed seed by seed into new territory. Wetlands expanded as rainfall patterns adjusted. Mammals crossed newly connected landscapes, occupying habitats that gradually became suitable. Populations shifted, reproduced, and changed over thousands of generations, while the climate continued its long climb toward a warmer equilibrium. The modern increase in atmospheric carbon dioxide belongs to a profoundly different rhythm. Since roughly 1750, industrial activity has released carbon into the atmosphere at a pace estimated to be 50 to 100 times faster than the Paleocene-Eocene thermal maximum. Comparable greenhouse conditions are developing within only a few human lifetimes instead of across countless millennia. The chemistry of the atmosphere is changing with extraordinary speed, compressing what once unfolded over ages into a brief interval of recorded history. Rate, more than destination, determines how living systems respond. A forest cannot relocate as quickly as weather patterns shift. Mature trees remain rooted where they first emerged, depending upon gradual generations of seedlings to expand their range. Animals that reproduce slowly cannot accumulate new adaptations within a handful of decades. Entire ecological communities advance only as rapidly as their least mobile members. When climate changes more quickly than those natural rhythms, landscapes begin separating from the organisms that once fit them. Even the Paleocene-Eocene thermal maximum carried biological costs. Marine ecosystems experienced significant extinctions, especially among organisms sensitive to warming oceans and changing chemistry. Yet the same interval also witnessed remarkable diversification among mammals, whose expanding ranges and evolving forms filled newly available environments. Change arrived rapidly enough to reshape evolution, while still leaving room for migration, adaptation, and ecological assembly over thousands of years. Nothing presently known from the 66 million years of the Cenozoic era matches the modern pace of atmospheric carbon release. Earlier greenhouse episodes, volcanic eruptions, and methane-driven warming events all unfolded more gradually than the transformation now measured by instruments around the world. The rocks preserve many examples of climates becoming warmer. They do not preserve another episode where greenhouse gases accumulated at the present observed rate through natural processes. That distinction defines both the strength and the limit of the Eocene comparison. The ancient Arctic reveals the physical appearance of a greenhouse planet after warmth has become established. It demonstrates that forests can reach the polar regions and that permanent ice can disappear from the north. Those conclusions rest securely within the geological record. The record grows less certain when the question shifts from destination to velocity. The Eocene provides a map showing where sustained greenhouse conditions can lead. It cannot reveal how living communities navigate a journey unfolding at a pace the rocks themselves have never recorded. The landscape outside the excavation appears timeless. Ice spreads across the ground, frozen slopes rise toward the horizon, and the mind easily accepts that this has always been the natural face of the Arctic. Geological history offers a different perspective. The frozen world surrounding modern researchers is not an eternal condition. It is a comparatively recent chapter resting upon a far older story written in rock beneath the ice. The ice sheet that now blankets Ellesmere Island began developing around 2,600,000 years ago, at the beginning of the Pleistocene ice ages. Measured against ordinary experience, that span feels immense. Measured against Earth's history, it is surprisingly brief. The evolutionary branch leading toward modern humans separated from the other great apes roughly 6 to 7 million years ago. Our own family history therefore reaches farther into the past than the permanent Arctic ice covering this northern land today. That comparison reshapes familiar assumptions. Between the disappearance of the rainforest, roughly 34 million years ago, and the arrival of enduring Arctic ice, around 2,600,000 years ago, more than 31 million years passed without a lasting continental ice sheet occupying this region. The climate had become cooler than the greenhouse world that came before, yet year after year, the Arctic still avoided the permanent frozen cover that modern maps encourage us to imagine as inevitable. Seen across that broader interval, permanence becomes a matter of perspective. The ice that appears fixed, the ice recorded by satellites, explored by expeditions, and remembered throughout human history, has occupied only a small fraction of the time since the rainforest vanished. More than 95% of that long interval unfolded without the enduring blanket of ice that now defines the Arctic in the modern imagination. The rocks preserve this reversal with remarkable consistency. Coal seams speak of vanished forests, fossil pollen marks changing vegetation. River deposits reveal landscapes that continued evolving through millions of years before glaciers claimed them. Each layer reminds us that permanence in geology rarely means forever. It means only that a condition has lasted long enough for human memory to mistake it for the natural order. Human civilization emerged during an even narrower window. Agriculture, permanent settlements, written language, kingdoms, trade routes, and every modern society developed within approximately the last 10,000 years. A warm interval inside the continuing Pleistocene Ice Age. Every familiar coastline, productive farming region, navigable river, and stable seasonal rhythm inherited by civilization belongs to that comparatively brief climatic episode. Our understanding of a normal planet has therefore been shaped almost entirely within exceptional conditions. This perspective gives the Eocene record its scientific value. Those rocks are not attempting to predict tomorrow. They establish the physical boundaries of what Earth has already achieved. They document an Arctic without permanent polar ice, forests extending across high latitudes, rivers occupied by reptiles, and climates unlike those experienced by any human civilization. Every observation comes from preserved landscapes rather than speculation. The ancient rainforest does not argue that history repeats itself in identical form. It reminds us that the planet possesses a broader range of possible states than living memory can contain. The ice covering Ellesmere today is one chapter within that longer narrative, remarkable in its own right, yet never the entire story. A place can appear unchanging while carrying the memory of many different worlds. The Arctic is often imagined as the fixed northern heart of cold, a landscape whose frozen character reaches back without beginning. The rocks beneath its ice preserve another account. They describe a region that has worn more than one identity, each lasting millions of years before yielding to another shaped by the same physical laws. Across Earth's 4,500,000,000 year history, the climate has alternated repeatedly between greenhouse and icehouse states. These broad shifts are woven into the planet's long evolution. They are neither accidents nor departures from a stable design. They represent the climate system responding to changing concentrations of atmospheric carbon dioxide, continental arrangements, volcanic activity, ocean circulation, and countless interactions unfolding across deep time. Warm intervals and cold intervals have each occupied substantial chapters of that history. The present icehouse world, defined by enduring polar ice, cool high latitudes, and a strong temperature difference between the equator and the Arctic, has persisted for roughly 34 million years. That span stretches far beyond recorded history and dwarfs every civilization humanity has created. Geological time places it within a different perspective. Entire climate states have lasted longer, disappeared, and eventually been replaced by others without altering the underlying processes that govern the planet. Earlier chapters remain preserved across continents. Before the modern ice house stood the Eocene greenhouse, remembered in fossil forests, coal seams, and the unmistakable jaw of an alligator resting within Arctic rock. Earlier, still came the Cretaceous hothouse, when dinosaurs wandered forests above the Arctic Circle beneath skies free of permanent polar ice. Even farther into the past, alternating glacial episodes and warm climates appeared again and again as complex life continued adapting to changing conditions across hundreds of millions of years. Permanent polar ice, therefore, is not Earth's default condition. It exists only while atmospheric and oceanic conditions support its formation and survival. When those conditions shift beyond particular thresholds, ice expands or retreats according to the balance of energy reaching the surface. The planet does not preserve glaciers through preference. It preserves them only while the surrounding climate continues making them possible. Every species alive today has evolved within this icehouse setting. Their bodies, seasonal behaviors, migration patterns, reproductive cycles, and geographic ranges all reflect a world organized around cold oceans, permanent ice, and modern coastlines. Those adaptations fit the present climate with remarkable precision because evolution continually shapes organisms around the conditions they encounter, generation after generation. The same principle once governed the rainforest that flourished across Ellesmere Island. Warm adapted trees, crocodilians, browsing mammals, and every other resident belonged to the climate that surrounded them. Their success reflected the environment available at that moment in Earth's history. The organisms living today express an equally successful response to a different climatic chapter. Neither landscape is more authentic than the other. The frozen Arctic visible today is entirely real. The rainforest that occupied the same ground 52 million years ago was equally real. Earth carries no preference between those worlds. It responds to physics, chemistry, and time, allowing each climate to emerge when the conditions that sustain it come together, and allowing every age to leave its own unmistakable record in stone. Some discoveries change understanding through numbers. Others do it through weight. An alligator jaw resting in the palm of a scientist carries a peculiar kind of perspective. It is a solid object, no larger than expected, yet it belonged to an animal that slipped through warm Arctic wetlands 52 million years ago. The same land that now locks itself beneath snow and permafrost once supported that living body from season to season before preserving its remains through an almost unimaginable passage of time. Coal seams still thread across Ellesmere Island beneath exposed rock. Travelers can cross them without recognizing what lies below their boots. Those dark layers are compressed forests, accumulated leaves, trunks, roots, pollen, and countless fragments of vanished ecosystems pressed together over millions of years. Every step passes above landscapes that once gathered sunlight through broad canopies before settling into sediment and slowly becoming stone. The record has never disappeared. It has only changed form. The alligator jaw recovered during the expedition of 1975 rested within that changing landscape throughout every chapter that followed its burial. It remained in place before permanent Arctic ice existed. It remained while climates continued cooling across millions of years. It remained as glaciers eventually spread across the north, reshaping valleys and preserving the rock that enclosed it. Only when human hands carefully opened the surrounding stone did the specimen emerge once more into daylight after an absence longer than human imagination comfortably measures. Geological time rarely aligns with instinct. 52 million years appears as a number on a page until it is compared with familiar scales. Human civilization reaches back roughly 10,000 years through agriculture, cities, writing, and recorded history. The alligator jaw waited more than 5,000 times that interval before anyone saw it again. Entire civilizations could rise, flourish, disappear, and be forgotten thousands of times while that single fossil remained motionless within Arctic rock. Even so, the jaw itself belongs entirely to the present. Its mineral structure occupies space today. The calcium within it once strengthened the bones of a living reptile moving through warm channels lined with trees. Those same atoms survived burial, pressure, freezing, and excavation. They now rest inside carefully organized museum collections in Pittsburgh, available for study by researchers separated from that animal by 52 million years, but connected through the uninterrupted continuity of matter. Few scientific disciplines offer this particular experience. A fossil is neither replica nor symbol. It is part of an individual life that genuinely unfolded under an unfamiliar sky. Tooth marks, growth patterns, and worn surfaces formed while muscles moved and food was consumed. The object held in modern hands participated directly in a vanished ecosystem before becoming evidence that the ecosystem itself truly existed. The alligator whose jaw emerged from Ellesmere Island breathed polar air warmed by a greenhouse climate. It fed, rested, reproduced, and endured months without sunlight as generations before it had done. Eventually it died, settling into sediment that would protect its remains more faithfully than memory ever could. When Mary Dawson lifted that jaw from Arctic permafrost in 1975, the frozen ground did not surrender a curiosity, it returned a witness. Ice had never erased the animal's existence. It had guarded the record until someone learned how to read it, allowing one living hand to meet another life separated only by the patient passage of deep time. Some histories survive in books, others remain inside stone, carried across immense spans of time until someone learns how to recognize the language they preserve. Across Ellesmere Island, dark coal seams run through the bedrock beneath the modern ice. At first glance, they appear to be ordinary bands of black rock. In truth, they are the compressed remains of a rainforest that flourished in the Arctic long before permanent ice arrived. The carbon within those seams once formed leaves, bark, roots, branches, and towering trunks that gathered sunlight through countless growing seasons. Coal is not an abstract material. It is former life transformed by geological time. Throughout the Eocene, fallen vegetation accumulated across saturated wetlands where plant matter built up faster than it could fully decay. Fresh layers settled over older ones year after year, sealing them away beneath mud and sediment. As burial continued, pressure increased, and chemical changes slowly reshaped the organic material. Millions of years passed before those forests became dense black coal. Every stage followed ordinary physical processes, repeated with extraordinary patience until an entire living ecosystem entered the bedrock beneath the Arctic landscape. Those seams, therefore, represent far more than a mineral deposit. They are the rainforest itself in another form. Carbon atoms that once circulated through magnolia leaves, swamp cypress bark, redwood roots, and flowering shrubs remain inside the island where those plants once grew. The living forest disappeared from sight, yet its substance never departed. Matter changed its arrangement while preserving the physical memory of an environment that thrived through months of winter darkness and long summers filled with continuous daylight. Researchers sometimes recover pieces of fossil wood directly from these layers and examine them under powerful microscopes. Within certain specimens, the original cellular structure remains visible after mineral replacement. Water conducting vessels, growth patterns, and microscopic anatomy survive clearly enough that paleobotanists can identify the kind of tree from which the sample originated. Chemistry transformed the wood into stone, yet the architecture built by living cells still endures. The forest continues to describe itself through details too small for the unaided eye, waiting for careful observation instead of imagination. The carbon preserved inside Ellesmere coal followed an equally remarkable journey. Before entering a tree, it drifted through the atmosphere as carbon dioxide. Through photosynthesis, the forest gathered that carbon into wood, roots, seeds, and leaves over millions of years. After cooling reshaped the planet, burial protected much of that carbon from returning to the atmosphere. Another 34 million years passed as compression completed its work. The result is a vast geological archive, every seam preserving another page in the long history of changing climates and shifting ecosystems. Near Strathcona Fjord, another part of that history remains exposed. Fossil tree stumps still project from the ground where erosion has uncovered them. A visitor can place a hand upon wood that grew above the Arctic Circle 52 million years ago. The trunks no longer produce leaves or cast shade, yet they remain rooted where the forest once stood, connected to the same landscape despite every transformation that followed. Time did not erase these trees, it altered their chemistry, buried their forms, and folded them into the crust of the earth. The forest still rests inside the island, preserved as coal, fossil wood, and mineralized tissue. Every dark seam beneath the Arctic holds the memory of a vanished world, carrying forward the carbon, structure, and history of a rainforest that endured for millions of years before becoming part of the rock itself. The oldest witness in this story has never spoken. It has never argued, celebrated, or mourned. It has only endured. Beneath the ice of Ellesmere Island, the rock still carries the record of a rainforest that flourished where snow now gathers, preserving each chapter with a patience measured across millions of years. The Eocene Arctic rainforest did not appear for a fleeting moment in Earth's history. It endured across millions of years, becoming a stable, intricate world filled with relationships refined through time. Forest canopies stretched across broad floodplains. Rivers carried warmth instead of ice. Countless generations of plants and animals were born, fed, reproduced, and disappeared into the same living landscape. By human standards, no civilization has approached such longevity. The forest became an ordinary part of the planet because it remained for so long. Its inhabitants were equally complete. Alligators moved through warm waterways. Tortoises crossed damp ground beneath towering trees. Primates climbed through leafy branches during months of continuous daylight. Coryphodon wandered through wetlands, its heavy body shaped for browsing among abundant vegetation. Every species belonged to an ecosystem operating with remarkable balance. Nothing about this community was unfinished or experimental. Evolution had already spent millions of years refining lives that matched the conditions surrounding them. Eventually, the atmosphere changed. Carbon dioxide gradually declined, temperatures fell, and familiar habitats contracted. Warmth withdrew from the highest latitudes, carrying entire ecosystems southward as each generation occupied a narrower range than the one before it. Species disappeared from the Arctic one by one until the forest itself no longer found conditions suitable for survival. No single morning marked its ending. The transformation unfolded across spans of time so immense that countless lifetimes passed before its conclusion became complete. What remained never truly vanished. Coal formed within the bedrock, fossil teeth settled into ancient river sediments, tree stumps persisted beside Strathcona Fjord. Mineralized wood preserved the cellular architecture of trunks that once gathered sunlight above the Arctic Circle. An alligator jaw rested beneath accumulating sediment until human hands uncovered it after 52 million years. Each discovery became another sentence in a story that had continued without witnesses for ages beyond imagination. The arrival of permanent Arctic ice did not represent the final page. It became another phase in a planet that has always shifted between different climate states. Earth has never possessed a single permanent identity. Conditions endure for immense intervals, then yield to new conditions when atmospheric balance changes enough to cross another threshold. The rainforest belonged to one chapter. The frozen Arctic belongs to another. Both are authentic expressions of the same world, following the same physical laws. Today, the Arctic continues to change. The forces shaping its future remain the same forces that assembled the rainforest and later transformed it into coal beneath the island. Carbon dioxide in the atmosphere, the reflectivity of ice and land, the movement of oceans, and the circulation of heat continue to guide the planet through processes that began long before humanity entered the story. Everything rests together beneath Ellesmere Island: the forest, the coal, the fossil wood, the alligator jaw, the tree stumps, and the ice are parts of one continuous history written across deep time. The Arctic remembers every chapter because the rock has carried each one forward without interruption. Long after living voices disappeared, the record remained. It still remains, waiting for anyone willing to listen to what stone has preserved across 52 million years.